I'm very happy to be here to share our work, which is enabling portable and high-performance NIC programs with Alkali. So this is a project collaborate with folks from UT Austin and UC San Diego. So as SmartNICs are becoming more commonly used in today's data center, we are seeing two major trends. First, the scope of SmartNIC application is expanding, with more complex network infrastructure service such as transport and load balancing being offloaded to the NIC. Second, the hardware landscape is also evolving very fast. New types of SmartNICs showing every year, and we come with new microarchitectures and new capabilities. However, this rapid growth brings new challenge, which is the intensified programming barriers. Programming and optimizing these diverse applications on these heterogeneous hardwares becoming more and more difficult. And we are seeing that programming barriers are becoming the major roadblock that prevents SmartNIC being further adopted. So there are two main barriers coming out. The first barrier is low-level parallel programming. Take the Agilo SmartNICs as an example. You can see these NICs come with 64 micro engines and 4 different memory layers and some fixed function hardware modules. To program these SmartNICs, the vendor provided an SDK with more than 500 different low-level libc functions. And as a programmer, if you want to implement some application on the NIC, such as implement the TCP transport offload, you need to manually parallelize this program across this massive amount of micro engines, as well as map your program state across these memory layers. So what it ends up is you are writing thousands of lines of low-level hardware codes, with most of the lines of code are writing the low-level parallel optimizations, but little of them are expressing the core processing logic. However, this is not the end of the nightmare, and the second barrier comes out is non-portabilities. As we said, new SmartNICs come out every year, and it's important for us to port one applications to a new generation of SmartNICs to prevent vendor locking. However, porting programs is extremely hard, not only because these NICs come with different vendor-specific low-level interfaces, but also because these NICs has completely different microarchitectures with different degree of hardware parallelisms and memory hierarchies. So, which means you need to re-implement all your previous parallel optimizations on new hardware. So what should be the ideal programming framework? There are 3 requirements. The first requirement is target agnostic programming. That is, the programmer should use their favorite high-level language to implement the program without learning the microarchitectures. And the second is portability and performance, which means your program should be able taken by a compiler and compile to all these NICs with good performance. And the last one is extensibilities, which means every time when a new SmartNICs come out into the market, it should incur minimal development effort in extending your compiler supporting this new hardware. So to achieve this ideal world, we have built Alkali, which is a multi-target NIC compilation framework. And the key enabler of Alkali are twofold. First, we use a new intermediate representation layer inside the compiler, which could serve as a narrow-width abstraction for building flexible and reusable compiler infrastructure for NICs. And we have developed a new auto-parallelization optimizations that could automatically port your program to different NICs with good performance. So here I show you the more detail of how Alkali works. As an Alkali developer, you will first write single-threaded, event-driven programs using your favorite high-level language. When writing the program, you will import the target NIC's architecture specification, and you will focus on expressing the high-level functionalities instead of worrying about the low-level microarchitecture details. So this achieves target-agnostic programming. The program will be taken by the compiler and converted into a special types of intermediate representation called alpha IR, which uses an event handler graph-based structure that captures the inherent parallelism in NIC programs. The compiler uses auto-parallelization optimizer to transform the original single-threaded program into a semantic equivalent multi-threaded one that could run efficiently on the target NIC, and such transform is guided by the performance spec of the target NIC. This achieves portability and performance. The optimized IR graph is then sent to the target NIC's backend, where it generates the low-level code that can run on the target NICs. In Alkali, adding support to a new hardware, the effort is minimized. You just need to implement the code generation logic for the target NICs, as well as provide the architecture spec and the performance spec. So this achieves extensibility. So in today's talk, I'm going to first introduce the programming interface, and then I will introduce the alpha IR design and the auto-parallelization optimizations, and finally, I will go into the evaluation. So Alkali programmer will write run-to-completion, single-threaded program that focus on processing each types of hardware events. Here I show you an example program which processes the hardware events that is receive packets from the network. The program can also generate events such as initialize a DMA write operations. When writing the program, the programmer will import the architecture specification for the target NICs, which defines the supported types of hardware event on the hardware. So Alkali defines portability as following. If two NICs share the identical architecture specification, which means these two NICs has the identical hardware interface and functionalities, Alkali program can be ported to run on two NICs without modifications. So next, I will introduce the design of alpha IR. So the goal of alpha IR is to serve as a general representation that could capture the diverse parallel execution semantics on the SmartNICs. So we are seeing there are three main types of parallelism on SmartNIC. The first type of parallelism is packet parallelism. Thinking about you have the NIC that have these two compute units. The way you could run your program is to replicate your program across them, and by spreading packets across this compute unit, you can utilize the massive amount of hardware parallelism. However, packet parallelism comes with the drawbacks. That is, when these packets are accessing some network state, such as a flow table, these compute units are accessing the same memory and would lead to synchronization overheads. The second type of parallelism could overcome this problem, which is flow parallelism. That is, instead of spreading your packets, you spread your network flows among these compute units. And because each flow is accessing a different portion of the table, you can partition the table and avoid synchronization. However, flow parallelism is only useful when you have per flow state, but it's less useful when you have some global state that is shared across all these flows. So the last type of parallelism could help, which is pipeline parallelism. That is, you split the instruction and network state of your program across this compute unit and have your packet flow through in a pipeline and could support global state without synchronizations. But it incurs overhead that you need communication between your compute units. So as we see, there are three types of parallelism, and each of it has its own trade-offs. Alpha IR uses the event handler graph structure to capture these three types of parallelism, as well as their possible combinations. Inside the compiler, every program will be represented as such a handler graph, where each node of this graph represent the code blocks that running inside each NIC's compute units, and it could be replicated multiple times. The edge of the graph represent events, which events are generated by handler and could trigger computation in other handlers. An event controller is sitting between handler, where it is used to define the event steering rules and ordering rules. Use such controller, you could use that to express a flow steering rule and express flow parallelism. And finally, each handler could maintain some persistent state, which could use it to represent network state, such as flow table and counters. So such a structure allows us to express these three types of parallelism and also their possible combinations. Okay, so now I'm going to introduce how Alkali implements the auto-parallelizations over these IR structures. So initially, the user writes a single-threaded program, and such program will be first converted into a single handler with no parallelisms. So inside the optimizer, it will try to search all semantic equivalent IR graph, which each graph represents a different way to parallelize your program on the target NIC. And the goal of the search algorithm is trying to find an IR graph that offers the best throughput performance on the target SmartNICs. So when we are developing this optimizer, there are two key questions to answer. The first one is, how could we develop an algorithm that could help us to navigate the entire parallelism search space. And the second question is how could we improve the search efficiencies? So now let's see how could we explore the entire search space. Alkali used the iterative two-stage search algorithm to guide the search, where the first stage of the optimizer is the pipeline cut engine. It tries to search different ways to cut your handler into a multi-stage pipeline of handlers. And we model it as a graph cut problem. So here we show an input handler, and our algorithm will try to construct a network flow graph based on the data dependency among the instructions inside the handler. And by searching different ways to cut this network flow graph, we could find different ways to partition instructions between different handlers. So every time when a pipeline of handler being generated, it will be sent to the second stage, which is a mapping engine. And the goal is to try to find how could I replicate each handler in the pipeline. So the mapping engine models this as a constraint satisfaction problem, where it has a SMT solver that encodes the hardware constraints of the target NICs that includes the compute unit number, memory layers, and memory sizes. And it will try to find a feasible replication plan that fits the target hardware constraints. So every time when a plan is generated by the solver, its performance is evaluated by the performance model. The performance model takes the target hardware architecture specifications as parameter, such as it trying to evaluate the memory access time, the communication overhead between compute unit, and use that to compare different plans' performance, so that the solver could find the highest throughput plan. So this iteration between the loop between pipeline cut engine and mapping engine will continue until it has have a global optimized plan in the search space. So now we can see we have come up with a search algorithm that could explore all these different types of parallelisms. But however, the problem coming out is that once your program becomes large, the search space grows exponentially. Search through the large space is harmful because it increases your compilation time, but also requires you to build a highly complex performance model to rank different plans in the space. So luckily, Alkali finds that there are actually many obvious bad and incorrect plans in this space, so that we can easily identify it through domain knowledge. Therefore, by adding constraints to our search algorithm, we could prune these bad plans and only search for these good plans. So for example, one of the example bad plans we find out is that we find like if we split the persistent state between two pipeline stages, it will lead to a correctness issue because of the read after write hazard, so that we could add constraint to avoid searching through this plan by adding uncuttable regions. You can find in our paper that how we add more constraints to avoid search through other bad plans. So we have implemented Alkali C frontend, compiler, and backends, totaling 20 cases of C++ using the MLIR framework. And currently, we support 4 different NIC backends, including Agilo NICs, Bluefield 2, FPGA NICs, and Panic. And we have also built runtime libraries for each NICs, including the one managed dynamic memory allocations, event controlling like flow steering, and inter-compute unit communication. So in the evaluation, we are first trying to answer the question, does Alkali easy SmartNIC programming and provide good performance? So here I show an example of application we have implemented, which is TCP transport offload. And our baseline is an open source implementations that was originally developed on Agilo. This baseline was originally implemented using thousands of lines of micro C code. And in Alkali, you only need 300 lines of code to express the exact same functionalities. And the key difference here is, huge difference here is, as an Alkali programmer, you only need to write those high-level functionalities without worrying about the low-level parallelizations. And also, after compile to the actual hardware, we can see Alkali achieve very close performance to the expert implementations. And more importantly, the programming in Alkali can be unchanged compared to all different other NICs, and transform the parallelism of the program and extract performance from different hardware. So you can find in our paper that how we implement 4 more different applications on these 5 targets and compare it with other baseline and expert implementation, and all of them achieves less than 10% of performance gap. And the last part is what we are trying to answer is Alkali extensible. So here we marked the backend development effort, and you can see the times to adding a new backend only takes days and weeks. And the key reason here is we centralized all the important optimization in the common middle-end compilers. So in conclusion, Alkali uses an intermediate representation to abstract the common parallelism inside your NIC program. And using this IR, we have built optimizations that allows you to port your programs across different hardwares with good performance. So please check out our open source code where we have open sourced all of our implementations. Thank you so much.